Good morning, everybody. Glad to see all of you here. Before I start my talk, I want to congratulate the AC people who thought of this symposium and organized it, because, you know, when we think of ACC, rest of the world thinks of football and basketball and sports. It's good to see academic excellence being brought to the fore. And so I congratulate people who thought of this idea. And I hope that there is a lot more of this in the future. Today I'll talk about smart grid and integration of renewable energy. The previous speaker did an excellent job of covering several things that actually I don't have on my slide, so it's a really good compliment. And I'm glad that you spoke before me, because it will make my job that much easier. Before I start talking about the work that we are doing at the University of Florida, I just want to acknowledge all my collaborators who are involved in this work and on papers that I've written with them. Elian Bitar at Cornell, Kameshwar Pula and Praveen Varaya at Berkeley, Enrique Baines at Valladolid in Spain, Ram Rajgopal at Stanford, and Professor Fang at University of Florida. And actually, one of our joint students of Professor Fang and myself, Richard Guo, is in the audience, and in fact, he presented some of our work at the poster last night. And I also want to acknowledge support from National Science Foundation and Florida Energy Systems Consortium that supported this work. So outline of my talk is I'll talk a bit about the grid, and as I said, our previous speaker did an excellent job. I won't speak much about the smart grid except how it relates to what we are doing. Talk a fair bit about renewable generation, then grid integration, a bit about storage, and hopefully all this in 23 minutes left. So electric grid, as was mentioned before, you can think of it in two major parts. The transmission grid, which is high voltage, and that's a mesh network. So there are loops in the transmission grid. So this basically takes power from centralized 500 megawatt or a gigawatt generator, a nuclear or a coal or a natural gas plant or a hydro plant, and transmits that power over high voltage lines closer to where it is used, which is our homes, our businesses, our offices, and our factories. Then you have the distribution network, which is near the edge, and typically these are radial networks. So there are no loops in these, and you want to think here the substation that comes near your house, and from there power gets routed to all our houses, and generally speaking there are no loops in that. So power just flows one way, and there are no cycles. This is, we like to think of it as a socio-economic, technical, dynamical system with phenomena at many time scales. So it's, as was mentioned, is the largest engineered system on this planet is the Eastern Interconnect, which connects all the generation and all the consumption east of the Rockies in North America. And it's so if you think of machines that actually work together as a single system, this is the largest single system that's ever been built. And it has phenomena at many time scales. They range from milliseconds to years. So let me just cover two ends. Milliseconds is all the protection stuff. So when a lightning strikes Gainesville, Florida, lines go down and things get tripped, and that all happens in very fast time scales. Like I said, milliseconds. What happens on the yearly time scale? All the planning. So suppose the utility wants to build a transmission line. That will take years of planning and then construction. So, and then there's everything in between. So this socio-economic technical system operates on these many time scales, and it's also geographically distributed. So you're talking about thousands of miles wide system all connected together and operating on these time scales. So both spatially and temporally, it's a distributed system. Extremely complicated. At least as of today, electric energy storage is really, really expensive. This is the big holy grail of work going on at Department of Energy, at National Science Foundation, and elsewhere. But fact of the matter is, today it's very difficult to store except for hydro. Pumped hydro is the only thing that's really capable of storing at utility scale multi-megawatt hours of energy at cost-effective prices. And finally, and this is what makes the problem extremely difficult and extremely challenging engineering problem. In this system, you must consume what you produce every second because you cannot store. So whatever is produced on a second-by-second basis must be consumed. Now, just to realize how difficult this question is, when I turn my light on and off, I don't ask anybody, okay? When a company turns its motors on, they don't ask anybody, just do it. So how does the generator know what to produce? Because the consumption is random. This is the beauty of what power systems people have managed to do in the last 80 years. So the way it is done is there is a very complex hierarchical distributed control system that has evolved over the years to manage this problem. This is called the power balance problem. So balance generation and consumption on a second-by-second basis. The approach so far has been adjust supply to meet demand. So demand varies randomly. Why? Because we all make our random decisions on when to consume what. Supply is adjusted at various generators to meet this random demand. And that's the paradigm. And you want to do this reliably, completely reliably, so no lights go out almost ever. There is natural uncertainty in consumption, the load, and the way you manage this is through what is called reserve capacity. So you have a lot of generation on reserve that is used and brought online at various time scales to meet this random changing demand. And it is done through a number of control operations which start with day-ahead schedules. So you plan for tomorrow's generation today and schedule all your generation for tomorrow, and then when real time arrives, make adjustments. So you can think of it, if you're a control type person, you think of it like, lots of open loop planning and open loop control, and ultimately some amount of feedback control at the very, very end. So in real time, you have 5-minute schedules, 15 minutes ahead. And ultimately, within 5 minutes, you have automatic generation control using system frequency. System frequency is an excellent indicator of imbalance between generation and supply. So if it's 60 hertz, you are doing well. If it goes low, you got too little generation. If it's high, you got too much generation. So you use that frequency as the final adjustment. And finally, because of deregulation of the electricity sector, there is now a unique mix of engineering economics because all this generation must be done through competitive electricity markets. Enter the smart grid, which is to impose on this power grid a network of sensors, communications, hardware of power electronics that was discussed at length earlier, computation and control to achieve reliability. A lot of discussion was presented on smart grid. Let me just present to you Steve Chu, our Energy Secretary's vision. Stronger, smarter, more efficient electricity infrastructure that will encourage growth in renewable energy resources, empower consumers, and lay the foundation of a sustained long-term economic expansion. What I'm going to focus on is renewable energy sources. So that piece of smart grid that is supposed to encourage renewable energy resources. Just to put things in perspective, this is 2011 data. 2012 data should be coming up or is probably already available. I haven't checked. This is the current state of US generation. Coal is 42%. That has changed a lot in the last year because natural gas is so cheap. So natural gas is, I'm sure, higher than 25% today. Nuclear is 19%. There is some petroleum, and renewable is 13%. If you break renewable down, it's mostly hydro. So 65% is hydro. 22% is, 23% is wind, and solar is less than 1% of the 13%. Okay, so we are really very far from getting anywhere near where we want to be in terms of using renewables. And one of the major reasons, and this is kind of hinted at in the previous talk, is renewable generation is not where people live. So if you look at wind resources, a lot of wind resources in the Midwest, going all the way from Minnesota, Iowa, North Dakota, all the way down to Texas. There's enormous amount of wind power, but not very many people live there. And how do you get all that wind power to the East Coast, or in case of California and Southern California, from to the West Coast? There is a lot of wind offshore, But that is gone. I mean, that's a major area of activity, and over time, I believe that offshore wind will also become feasible, including Florida. I mean, there is offshore wind in Florida as well. Solar is a similar story in terms of a lot of solar energy resources are not where people live, but generally, you need transmission capacity to move all this renewable energy to where people live. Wind capacity has been growing very, very nicely. In fact, wind has been the single largest installation for the last at least 2 years. So the data just came out for 2012 a few weeks ago. And again, wind was the #1 electric energy generation installed. Solar is also picking up, but it's not even close in terms of installed capacity. PV installation is also growing very, very fast as prices come down, and especially if the Sunshot, DOE Sunshot initiative is successful, which is dollar per watt installed. I think we will see a huge growth in PV as well. So again, both are growing very fast, although from relatively small bases. So it looks good when you look at these charts, but you go back and remember, solar is less than 1% of the renewable. Okay? So we have a long way to go. This is the renewable energy generation, and again, wind is picking up very significantly. Solar doesn't even show up on this chart because it's on percentage basis, but it's also growing. Now I want to come to the heart of the problem that we have worked on, and that's the variability. One of the major problems with renewables is that the power output of a renewable source varies in all time scales. So it clearly varies at the second. I mean, basically, if you look at wind or solar, it depends upon how much wind is blowing and how much sun is shining. So if a cloud passes, your output will drop. If the wind slows down, your output will drop. It picks up, output goes up. So it certainly varies, you can imagine, in the seconds and minutes and possibly even hours time scale, because we experience it. Suddenly, solar power is going to go down to 0 at night because there is no sunshine. What is interesting is that it even varies at annual time scales. So if you think about the total energy produced by a wind generator this year versus last year, total output will be different. So there is randomness at the annual time scale. It's a very beautiful set of charts. These are 30 days in June of 2006 in the Tehachapi region of California. Each color is a day. Okay? Each color in this plot is a single day in the month of June. You can see that every day is different from every other day. There is no, and so that solid line is supposed to be the average. There is no average day. So anybody or any planning that is done with this average would be total failure. So intermittency, uncontrollability, and uncertainty, these are the principal causes of difficulty in integrating renewables into the grid. Why? Because remember, our paradigm is control the generation to meet the random demand. Well, my generation now is random. What am I going to do? That's the heart of the problem. Same thing with solar. Okay, this is still wind resources. Or maybe the top graph has some solar. So one interesting thing is wind and solar complement each other. So when the sun is shining and it's really hot, wind goes down. So when wind goes down, solar can pick up. So in some sense, there is some hope of complementarity between solar and wind. So if you have the right amount of wind and solar installation, maybe you can smooth out some of the variability. The other problem is tremendous ramps that can happen in wind and solar outputs. So you can go from, say, 10% output to 80% output in less than an hour. So suppose you had a 100 megawatt wind farm. Your output can go from 10 megawatts to 90 megawatts in an hour. Well, if that happens, somebody else has to take the slack. Okay? So if wind ramps up, somebody has to go down. Why? Because I must keep generation and supply in balance all the time, second by second. That's the problem. So there are three distinct issues. Uncertainty, which is you can't predict what you are going to get. Okay? You cannot predict what you are going to get because of randomness. Let's say that problem went away, that I was like God, and I could predict the weather. Okay? suppose I could do that. There is still uncontrollability. I cannot control it. So I know what is going to happen, but that's what I know. I still cannot control it. And the third thing is intermittency, that it can go from 0 to full, and it can stay at 0 for days together. So there are data sets where output of a wind farm was close to 0 for days in a row. If that happens, imagine the difficulty, because that means you cannot count on that power production. So you must have some other generator to meet your demand. So this phrase, variable generation, captures all three aspects into a single phrase. Just to illustrate the impact of this variability, there is this notion of capacity credit. And first I'll explain to you what this is. There is an agency called NERC, North American Electricity Reliability Corporation. And the reliability requirements are, you don't want to lose power for more than 1 day in 10 years. Okay? So that's sort of the reliability expectation from electricity system. Pretty amazing, okay? So you want to have enough capacity so that you will not lose power for more than one day in 10 years. So how do you achieve this? So you have plenty of capacity, typically 115% of the peak load. So if you look at the peak load, which is summer afternoons, you find out how much total load you have in your system, and then you have capacity that's at least 15% above. And that's typically how this is managed. Now break that down further. So I've got like hundreds of generators, some coal, some gas, some nuclear, some hydro, and some renewables. You can ask the question, and every generator goes down. If for nothing, no other reason, just routine maintenance. Okay, so for routine, you must take it down. So you can ask the question, if I have say 500 megawatt nuclear generator, how much credit can I give that generator toward reliable availability? Typically for a nuclear, you will get 90%, because they rarely go down. I mean, they will be taken out sometimes, but you get a pretty high capacity credit for it. Same with coal, same with natural gas, same with hydro. You get pretty high capacity values. So you take all your generators, multiply with their capacity values, and make sure that you have enough generation to meet your demand on the worst day and still have 15% margin. That's how this system is managed. Ask the question, so capacity credit is the fraction of the nameplate capacity. Okay, so I have a 500 megawatt generator. What credit am I going to give it? Is it 450, 400, 420, 430? And you get paid for it. Ask yourself, I built a 500 megawatt wind farm. How much capacity credit should it be given? Well, this problem has been looked at, and I just got some numbers for you. So a lot of utilities and system operators have looked at it. Just some numbers just to kind of how bad the problem is. PJM, which is the Pennsylvania, Jersey, Maryland ISO, MISO, which is the Midwest Independent System Operator, 13% capacity, 30% credit. So if you build a 500 megawatt wind farm, you get 65 megawatt worth of credit. That means I can only count on you for 65 megawatts. I can't count on you for the rest of this. New York ISO, 10%. SPP, which is the Southern Power Pool, 10%. E.ON is the big German utility. Huge amount of wind installation, 8%. And this problem could even get worse at high penetration. So now, just to kind of present you the problem in its full glory, suppose you want 30% renewable energy. Given the fact that a typical wind farm will produce 30% energy on an annual basis, so you must build 90% of your needed energy need in nameplate capacity. Why? Because you only produce about 30% on average. So you must build 3 times as much, roughly 3 times as much to meet your total energy needs. So you will have installed nameplate capacity, which is practically 100% of your need. There will be times when wind will blow and will produce that 100% of your energy. What happens to the rest of it? What happens to the coal? What happens to natural gas? What happens to the nuclear? You can't turn those things down. Somebody is going to have to go down. This problem has not been totally faced up. And I think this, so I'm going to, since I'm running short on time, I'm going to, so forecasting is a huge problem and enormous opportunity. Lot of large-scale studies have been done in the last few years. Eastern Wind Interconnect study, EWITS, Western Interconnect study, HISO, which is the California system operator, and so on and so forth. General conclusions seem to be that if we put enough transmission capacity, we can go up to 20 to 30% renewable with significant impact on power system operations. Implications for markets, electricity markets, reserves, how much reserve do I need to keep on hand to meet my reliability? Balancing areas, these are the areas where you must supply generation and consumption. Flexibility of the production stack, if wind goes up, who is going to come down? So I must have flexibility in my production stack. Fast ramping resources, because remember, wind can go from 0 to or 10 to 90 in like an hour. Who's going to come down or who's going to go up? Storage and adjustable demand. This is what we have worked on. So all this work that we have done in the last few years is basically answering pieces of this puzzle. So I know I'm running short on time, so I'm not going to cover the rest of it. Let me just kind of flash through. One of our main results is, so we do a lot of work is, just stochastic. If you want to think of just a single phrase, that what we do is stochastic optimization. Because there's a lot of randomness, and you have a lot of control variables. So how do you large-scale stochastic optimization? So this is one example where we show that the optimal policy is a quantile policy. So you look at the probability distribution function and calculate the inverse, and that gives you the optimal control. We have worked on storage. We take a simple storage model where you have some loss of energy over time, and then you can inject power or extract power. And the problem we work on is, at each time instant, how much to extract from storage and how much to inject in the storage, which is a stochastic dynamic programming problem, which we solve. And we got nice results on that. And I know that Richard presented his poster, which is along the same lines when we bring in distributed resources. We have worked on benefits of aggregation because randomness reduces if you average lots of uncorrelated random sources. So we have worked on that. And I want to conclude in the remaining 2 minutes by kind of connecting my talk to what was presented before. The paradigm until now has been adjust your supply to meet random demand. Well, we now recognize that our supply is random. So the paradigm is going to be adjust a random supply to a random demand. So match two random quantities instead of having one controllable quantity meeting a random quantity. So manage to equate two random quantities. And way to do that would be to make demand adjustable as much as supply is adjustable. So make both of these things adjustable plus some randomness. So you have some adjustable parameter, some random parameter. Together, we can try and balance. So idea of flexible controllable demand, things like our HVAC system or refrigeration or water heaters. With the right kind of smart power electronics, we can adjust the demand to meet the randomness. So how can we, so there's a beautiful, very important fundamental research questions that are just beginning to be addressed. So I see 10 to 15 years worth of excellent work that is going to get done in this space where imagine the number of refrigerators in the country, okay, at least 150 million, at least. Imagine the number of HVAC units. So you got this extremely large number of units out there that could potentially be adjusted. What algorithms, what computational architectures, what communication architectures, and what power electronics will come together to control these millions and millions and millions of devices to solve this power system problem. And I think this is not quite the internet scale, because internet scale is you got everybody with 5 smartphones now. So it's like, but this is getting close to that scale of problem. The big difference being real-time nature of the problem. This is all going to happen on a second-by-second basis. So this is why the problem is really, really hard, and it's So these are just our papers that we have published, and I'm going to stop here exactly at 0, 0, 0. Thank you very much.
Now it's 0, 0, 0. Thank you, Pramod. Do we have time for a few questions there? It's hard for me to see in the light.
There is one over
right there.
So according to your talk, which I appreciate, it's a very good talk, why is the option of energy storage not very, in your talk, it's not really part of your talk. You're talking about, variable supply and use. You've not talked about storage of that so that, when the supply is variable, then you can have use when it's not there.
Okay. So two responses. One, I did have some slides on storage. So we have worked on storage optimization. It's a stochastic dynamic programming problem. So that's sort of the technical answer. The real practical answer is that storage is still very expensive. So it's not realistic with today's pricing of batteries to store hundreds of megawatt hours of energy in a cost-effective manner. So Department of Energy has this as one of its major initiatives. Currently, I work at ARPA-E, and one of our major initiatives is $100 per kilowatt hour storage system. So if you can bring the storage cost down, this problem becomes dramatically different. So if we can make storage really cheap, then a lot of the things that I've talked about will change very significantly. But we are not there yet. And if research succeeds and we have commercial scale deployment of large scale storage, then the problem does become very different and much more tractable.
We have one over here.
I was curious, the wind power generation you showed is a pretty local spot. As wind power becomes more, nationwide, would you not expect the energy generation to level out and to get more of an average all the time?
It is certainly true that if you average over larger and larger areas, the variability does decrease. But you'll be surprised that even over large areas, you still have significant variability. Like I said, there have been large wind farms covering significant area where average was 0 for several days in a row. Second, you have these weather fronts. So when a weather front goes, say, from Midwest, say, Minnesota to Chicago to Detroit and on to East Coast, the wind power output will go through these ramps in a successive fashion over the next 8 to 10 hours to the next day or 2 days. So yes, there is no question. In fact, one of our papers is on how to use aggregation of large numbers of random sources to reduce variability and its impact. It still doesn't, it's not going to completely eliminate the randomness. And in case of solar, you still have half the day.
Pramod, I had a question on there.
Yeah.
I mean, in fact, it's related to the storage part. I mean, do you foresee what percentage of that variability do you see eventually being reduced say, in the next 10 or 20 years?
I think if the DOE goals on storage costs are realized, then I would say, 30, 40, 50% of the problem could be solved by cost-effective storage. But I think it all depends upon how cheap can we make storage, and then the material impact. So if you're going to use lithium ion, then the pressure if you start building this stuff, the problem with energy is only one, and it is scale. The scale of this problem is so humongous that once you start to say, okay, I'm going to start storing, and you build it on scale, suddenly you might have resource problems that aren't obvious today. So, but I think storage is certainly a major opportunity. No question about it.
Thank you, Pramod.
Thank you very much.